Hello, this is Jack Jackson. In this video, we're going to talk about how to find arc length of a curve where it's defined as a function of x. So antiderivatives are accumulation functions. They accumulate values of the definite integral from some point up to the input value of x. We've used definite integrals to accumulate areas and to accumulate volumes. We can also use them to accumulate distances along a curve. In other words, we want to use a definite integral to measure the arc length of a curve. So the basic question is, how do we measure arc length s along some curve defined by a function? Well, informally, we just take a flexible ruler, a tape measure, and have it follow the path exactly. We then just measure the length with this tape measure. Unfortunately, we do not yet have a formula for measuring distance this way, based on the formulas. However, we do have a basic formula for computing the straight line distance between 2 points. As with other integration applications, what we do is start by dividing up what we have into smaller pieces and approximating with a pre-calculus thing. In this case, we start by dividing up the path into subpaths and approximate the length of the subpath with something we know, the length of a secant line segment for that subpath. We add up these lengths to get a Riemann sum. We finally take a limit as the number of subintervals goes to infinity and their lengths go to 0 to get the definite integral, which produces the arc length. So here's an example of a function here, right here, and this function is it's actually x squared plus 1, and the part that we're interested in is from here to here, this arc length here. So it's going from the point 0, 1 to the point 2, 5. That point there. We want to know the length of that blue curve. And so what we're going to do is we're basically going to approximate that with a secant line segment like this. And the key to understanding how this is set up is to understand the relationship between delta x, delta y, and delta s. Delta x is this purple distance, the horizontal change. Delta y is the vertical change, the green one, and delta s is the change along the hypotenuse here, the red distance, or the length of that secant line segment. So we want to get this delta s either all in terms of x or all in terms of y. Okay, so if the original function, say, is all in terms of x, then we see that we have a right triangle here, and we see that we have a Pythagorean relationship. So delta s is the square root of delta x squared plus delta y squared. Now, if we want to get everything in terms of x, we can multiply top and bottom of this, or we can multiply by the fraction, delta x over delta x. Another way to write that is delta x is the square root of delta x squared, at least if we got a positive, even without a positive delta x. Yes, if delta x is positive, that works. So the delta x we're going to leave on the top, we're going to leave outside, and we're going to distribute the square root inside here. Well, square root over square root is one big square root. So we have delta x squared plus delta y squared divided by delta x squared, and distribute. Delta x squared divided by delta x squared is 1, and delta y squared over delta x squared is delta y over delta x squared. Now, if instead we had x as a function of y, we'd want to get everything in terms of y. We'd start out the same, but we'd multiply by delta y over the square root of delta y squared, and it would turn out to be this right here. Okay. So now what we want to do is we want to break this into some pieces, and on each piece we want to work this out. So we want to work out here. Here's one. Here's another one delta s, another delta s, another delta s. So we have a delta s1, a delta s2, delta s3. And so so an estimate would be to take all these delta s's and add them up. So we want to take s sub k, the delta s sub k's, and add them up from k equals 1 to n. In this case, I have 1, 2, 3, 4, looks like 4 subdivisions demonstrated here. Or 3, 1, 2, actually 1, 2, 3, 4. It says 3, but there's actually 4. Okay, and if we add up these secant line segments, what do we get? Well, we're adding up something that looks like this. Okay, and what are the setups here? Well, delta x is b minus a over n, just like usual. So a is the first x, b is the last x. So here a is 0, b is 2. B minus a over n is delta x. X sub k is a plus k delta x, so it's the x at the right end of each interval, just like we did for right Riemann sums. And then delta y is just f of x sub k minus f of x sub k minus 1 would be delta y. Okay? And that's a Riemann sum. So then what do we want to do? We want to take this and break it into smaller and smaller and smaller and smaller intervals with more and more and more and more of them. So here it is for 8, and here's 20. For 8, we're already getting a pretty good approximation. For 20, it's really hard to tell these little line segments apart from the actual curve. So the limit of this produces a definite integral giving the exact value of the arc length of the curve. The key is this relationship among the differentials dx, dy, and the arc length differential ds. ds is the square root of dx squared plus dy squared. And so what we did have here as a relationship among the sides, delta s is the square root of delta x squared plus delta y squared. And this is how we wrote it with the delta x out here or delta y out here. When we take the limits, all the delta x's basically become dx's, and all the delta y's become dy's, and the delta s becomes a ds. And so this gives us this basic setup. And so the s is the sum of those becomes an integral. It's an integral over that interval of ds, and we'll write it this way here if we have a function of y is a function of x. So then notice dy over dx is just the first derivative of y with respect to x. And we're integrating over x values. On the other hand, if you can get x as a function of y, you could use this version, integrate with respect to y, and dy over dx over dy is the derivative in the other direction. So let's do this to find that length of the arc along the curve f of x equals x squared plus 1 from 0 to 2. That's exactly this arc length up here in blue that we started with. Now, as a first rough estimate, notice it's quite a bit less than just adding these two together. This is 2 and that's 4. So definitely it's less than 6. It's going to be closer to this length here, which is the square root of 2 squared plus 4 squared. That's the square root of 20. Okay, and it's still less than the square root of 20. It's actually greater than the square root of 20. So that's a below estimate, and this is a above estimate. So somewhere between there. The square root of 20 is about 4.47, so that's going to be a rough estimate of what we expect to get. But it's going to be certainly between that and 6, and the 4.47 is a closer estimate. We see below it turns out to be about 4.65. So here's what we do. F of x is x squared plus 1. dy over dx is the derivative of that, which is just 2x. And we're going from 0 to 2. So the arc length, L or S, is given by this thing that we just set up here. And so that's 1 plus the derivative squared. And we want to integrate that from 1 to 2. From 1 to 2? 0 to 2. Yeah, 0 to 2 is what I want to do. I need to fix that. From 0 to 2. Now, I found this number here by just plugging this in a graphing calculator and having it do the integral. And it came up with that approximation. It's using a variation of Simpson's rule to get a decimal approximation. Because of the square root involved, these arc length integrals are often very difficult to compute exactly. It's very hard to find an antiderivative a lot of times. So it's not unusual for a homework or exam question to ask you to set up the appropriate integral and use technology to approximate its values. However, we can work out the details for this particular integral to find an exact values, and the details will follow. Here we first use a trigonometric substitution, and we obtain the integral of secant cubed of theta. And we're going to work out the details of just getting the integral of secant cubed and antiderivative of secant cubed of theta first. It requires integration by parts, and then we'll substitute this result at the appropriate point in the arc length integral. So we want to do, let's see, here's the integral of secant cubed. So we want to do the integral of secant cubed of, that should say, those should be all thetas, no x's here. Okay, so the integral of secant cubed theta d theta. We do it by parts. We let u be secant of theta and dv be secant square theta d theta. So we know how to do the antiderivative here. The antiderivative of secant square theta d theta is tangent theta. And then we know how to do the derivative here. The derivative of secant theta is secant theta tangent theta d theta. So this is the integral of u dv. Then we get uv, multiply these two, so that's secant theta tangent theta, minus the integral of v du. So you multiply these two together, and you get a secant theta and a tangent square of theta. It should be all thetas. Okay, now I think I got all the thetas where they're supposed to be. Okay, now tangent square of theta is secant square of theta minus 1. So distributing this, we get secant cubed of theta. That's going to be minus here, d theta. And then we get a secant theta here. There's a minus and a minus there makes plus secant theta. Now notice we have secant cubed theta on both sides. So we add, but they're different coefficients, positive 1 here, negative 1 here. So I'm going to add the opposite of that to both sides. So I'm going to add secant cubed of theta to both sides. It's going to cancel this out, and it's going to end up doubling up over here. Then I just divide by half to get secant cubed of theta by itself. Finally, I have to replace secant of theta d theta, that integral, with the natural log of the absolute value of secant theta plus tangent theta. Of course, there's plus c there. All right, now. All right, so here we have the arc length is the integral from a to b of the square root of 1 plus dy over dx squared dx. dy over dx is 2x, and we're going from 0 to 2. And this is a good form for a trig substitution. Often happens with these square roots. So that's the hypotenuse, and then this side is 2x and this side is 1. So 2x over 1 is the tangent of theta, x is 1/2 tangent theta. dx then is 1/2 secant square of theta, d theta. And the square root here over 1 is the secant of theta. So this square root becomes secant theta. The dx becomes 1/2 secant square theta d theta. And eventually we want to evaluate from x equals 0 to 2. Now if you look, this gives us a 1/2 out front, and the integral is secant of theta. So that's why we had to do this up here. So we're going to take this expression right here and replace it with the for the secant of theta, and that's what I did right here. These two halves multiply together to get a fourth. Now we got to go back to our triangle and substitute back in. So secant of theta is the square root here, square root of, let's call it 4x squared plus 1. Tangent of theta is the 2x over the 1, so that's just 2x. And secant theta again is that square root, and tangent theta again is the 2x. Now we're going to evaluate from 0 to 2. We still got our fourth out here. So you take all this and plug in a 2 everywhere there's an x. There, 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 there. Minus, plug in a 0 everywhere. Okay, let me do this last part here. 2 times 0 is 0. 0 squared is 0 times 4 is 0 plus 1 is 1. Square root of 1 is 1. 1 plus 0 is 1. Absolute value of that is 1. Log of 1 is 0. So that term goes away. And this has 0 times some other stuff, so that term goes away. So this last part's gone. Well, I'm working from the right, so let's keep coming back that way. This is 4. 2 squared is 4 times 4 is 16 plus 1, so that's the square root of 17. So that's the square root of 17 plus 4. That's already positive, so I can drop the absolute value. And there's a 4, and that's a square root of 17 again. So that's 4 times the square root of 17 there. I'm going to distribute the 1/4 and make it square root of 17 plus 1/4, the natural log of square root of 17 plus 4. Plug that in a calculator, you get that value right there. And I use this on a CAS calculator and I got the same thing, so that verifies that. So that's an example of how we can do an arc length integral.